talk about this. So you know what? Even though the ethanol is the exact same problem as we did for the methanol, we're going to calculate the density of ethanol and see if there's much of a difference. If there's not much of a difference between ethanol and methanol, then it's going to be hard to tell the difference. Do you have methanol? Do you have ethanol? If the densities are about the same, you don't know. You know. That is, are you drinking pure water? Or are you drinking contaminated water? If the densities are about the same, you can't tell by density. You have to tell by some other method, right? And so the density of methanol, 0.7914. Is that wind blowing in here? And so what is the density of methanol? And let's see. I'm going to leave the volume of the picnometer here. And so we're going to go to grams of ethanol. Ethanol is abbreviated ETOH. This. And when it's filled with ethanol, it's 33.470 grams. So 33.470 grams of picnometer plus ethanol minus the picnometer, which was 25.601 grams. And we're allowed 3 decimal places, so this is why I line it up like this. And what does that come out to? So 33.47 minus 25.601 equals 7.869. 7.869 grams. We're allowed 3 decimal places, so we have 4 sig figs in our answer here of ethanol. The volume is 9.969 milliliters, so the density of ethanol is going to be 7.869 grams divided by 9.969 milliliters. So divided by 9.969 milliliters. And that gives me a density of 0.78, oh not, yeah, 0.78935. How many sig figs am I allowed for this? 4. So I'm going to have to round one. So there are 2 ways to show that. One is 7893 sub 5. So if I'm doing subsequent calculations, I might use this. Or if I'm at the end, I just go 78934 grams per milliliter. Yeah. Okay. So can we tell the difference between ethanol and methanol using density? Well, it depends on how precise your measurement is. To 1 sig fig, what would this round to 1 sig fig? 0.8. And to 1 sig fig, this would round to 0.8. So if we only measured the density to 1 sig fig, could we tell the difference between ethanol and methanol? No. If we measured the density to 2 sig figs, what would this be? 0.79. This one would be 0.79. So if we measure the density to 2 sig figs, there's no way we could tell the difference. If we measure it to 3 sig figs, could we tell the difference? Yeah. Because this would be 0.789, this would be 0.791. So if we measured it to 3 sig figs, we might be able to tell the difference, but then there's experimental error and uncertainty, and that could screw things up. If we measure it to 4 sig figs, better. You know, the more sig figs, the more we can differentiate the 2. And so, since there is a slight difference in the density, you know, 7894 versus 7914, we can tell the difference. Now, if we have a mixture, if there's a difference, then we can do it via the graphical method. So the mixture is going to contain both ethanol and methanol. And so what we want to know is we want to know the percent methanol and the percent ethanol in this mixture. And this is going to be unknown, this is going to be unknown. And so what we have is we have 2 unknowns, x and y. If we have 2 unknowns, we need 2 equations. Or an alternate method. Whenever we have two unknown mixtures, we can also solve this using the graphical method. The graphical method, this isn't talked about in the book. It's just an alternate method that we can use to solve this. So the density of methanol was 0.7894 grams per milliliter. The density of ethanol is 0.7914 grams per milliliter. And so the graphical method does it like this. We can tell the difference between pure methanol and ethanol. Not only can we tell the difference between pure methanol and ethanol, we can also have a mixture and tell how much methanol and how much ethanol we have. The more ethanol we have, the higher the density. The more methanol we have, the lower the density. Can you see? Because the density vary like this. And so in the graphical method, this is how we do it. We look at which one's lower, and the smaller number is going to be methanol here. And so what we do is we assume 100% methanol. If this mixture consisted of 100% methanol, what would its density be? Well, its density would be 0.7894. And so we'll plug that in here. 0.7894. Okay, this is going to be the density of the mixture. So if it were 100% methanol, what percentage ethanol would it be? It would be 0% ethanol. And so this isn't a mixture, it's just methanol. Okay, then we go to the other extreme. What's the other extreme? The other extreme is 0% methanol. If we had 0% methanol, how much ethanol do we have? 100%. So if this were 100% ethanol, what would its density be? Well, its density would be 7914. So up here we have 0.7914 grams per milliliter, and that would be here. Now, the next thing we're going to do is we're going to assume it's linear. So the more ethanol we have, the heavier it is, the more dense it is. And we expect this to be linear. We don't expect it to be nonlinear. That is, maybe it stays flat and then shoots up. That's not going to happen because as we gradually increase the heavier ethanol molecules in there, the density should gradually increase as well. So here is the scientific method. We have our data. We look for patterns and trends. We see a trend line here. We see a linear trend line. And then we try to describe this mathematically. So if I have a line like this, what's a mathematical equation that fits a line? Yeah, and so the equation for this would be y is equal to mx plus b. So we're going to describe this relationship using that equation. And so y is going to be the density of the mixture. So we have the density of the mixture is equal to the slope. The slope is going to be delta y. And so delta y is 0.7914 minus 0.7894. This is going to be grams per milliliter of the mixture divided by delta x. Which one should we have as our x-axis? Do you want your x-axis to go from 100 to 0 or 0 to 100? 0 to 100. So we're going to use percent ethanol as our x. Was the ethanol more dense? Did I get that right? 0.7914? Yeah? Which one was more dense? Methanol or ethanol? Ethanol? Okay. Okay, and then down here it's going to be 100 minus 0% ethanol. plus the intercept. The intercept is going to be 0.7894 grams per milliliter mixture. All right, so let's go ahead and do this calculation. 7914 minus 7894 is going to be 0.0020. This is 20 difference here, grams per milliliter. 100 minus 0 is going to be 100% ethanol, plus B, 0.7894 grams per milliliter. And so this is 10 to the minus 3 divided by 10 to the minus 2. 10 to the positive 2, 10 to the minus 1. This is going to be quadruple 0 to 0 grams per milliliter per percent ethanol. .7894 grams per milliliter. Oops, times. I forgot something. It's mx. X is what? Percent ethanol. Sorry, enter it here, percent ethanol. And so this is M times X, which would be percent ethanol. So let's try this equation to see. If I had 0% ethanol, that would be 0 times M is 0. I get a density of 0.7894. So if I had 0% ethanol, I get the density of 0.7894. If I had 100% ethanol, so that would be 100 times this, which would be 0.002, plus this would be 0.7914. So if I had 0% ethanol, it works. Do you see it works? So I call this the graphical method because there are two ways we can do this. One, we could do this graphically. So for example, if I had 50% ethanol, I could do this graphically. Go to 50% ethanol, and then go over here and read the density. Actually, the density is going to be halfway between these two. You know, if I have 90% ethanol, I'd go here. 10% ethanol, I'd go here. So I could do that graphically. But I don't have to do it graphically because I have the mathematical equation. And so all I have to do is plug in the percent ethanol, and I can calculate the density. Or if I have the density, I can figure out how much percent ethanol I have. So let's do an example of one of those calculations. There's two calculations we can do. Let's say I have an unknown mixture, and I use the picnometer to measure its density. And the density came out to 0.7900. So an example of this is the density of the mixture came out to 0.7900 grams per milliliter. What is the percent methanol and what is the percent ethanol in this mixture? So if I want the percent methanol and percent ethanol, that's two unknowns. If I have two unknowns, I got to use two equations. But I already did this graphically. If I do this graphically, then I don't need two equations. I have this equation here that describes it. And the equation that describes it is the density of the mixture is equal to the slope, which is going to be quadruple 020 grams per milliliter per percent ethanol times the percent ethanol plus 0.7894 grams per milliliter. So I'm going to solve this equation for percent ethanol. So the percent ethanol is equal to, okay, this 0.79 minus this 0.7894 equals divided by this. So divided by quadruple 0.02. And that gives me 30.000% ethanol. Okay, now I got to figure out how many sig figs am I allowed for this. Now this is complicated for sig figs because it's a combination. I have some subtraction and I have some multiplication and division. And I should have done this in steps in order to figure out how many sig figs I'm allowed, because I got to keep track of this. So the first step I did was I took 0.7900 minus this. So I subtracted this from both sides. So I should have done that over here. Let's see, 0.7900 minus 0.7894. And this is going to give me 0.0006. I'm allowed 4 decimal places. If I'm allowed 4 decimal places, how many sig figs do I have in that? 1 sig fig. Okay, then I take that number and divide it by this. This has 2 sig figs. So if I take 1 sig fig divided by 2 sig figs, then I'm going to be allowed how many sig figs here? Just 1. So if I'm only allowed 1, I leave it like 30% or 3.0 times 10%. Or 30 with a little, no, actually that would be 2 sig figs, right? And this is 2 sig figs, sorry. It'd just be 3 times 10 to the first. Ethanol. Is that very precise? Not really. I mean, if there were a bigger difference, between the density of ethanol and methanol, then I'd get more digits here. And if I have more digits here, then I get more sig figs here. And so the precision, it looks like to be like 1 sig fig for precision. It's asking us how precisely could you determine the composition of an ethanol-methanol solution by measuring its density with a picnometer? Well, it's looking like maybe 1 sig fig precision. Okay. Maybe if we did it off the graph, we'd get more digits, precision. But 1, maybe 2, because it depends on the subtraction here. So 1 or 2 sig figs of precision. So if it's 30% ethanol, how much methanol do we have? 70%, because they have to add up to 100%. And so 30% ethanol, 70% methanol. Okay, so this is an example of the graphical method for solving these. So some of these problems are just trying to visualize what's happening. Let's take a look at the next problem here. 80. A picnometer weighs 25.60 grams empty. MT is often abbreviated MT. So this is just the picnometer. When filled with water at 20 degrees C, it weighs 35.55 grams. The density of water at 20 degrees C is 0.9982, so that's 4 sig figs. So this is the picnometer plus water. And so the first thing is, let's figure out how many grams of water there are. And so there's going to be 35.55 grams of picnometer and water, minus the picnometer, which weighs 25.60 grams, the picnometer. And that's going to give us 5, 15 from 6 is 9, 14.5 is 9.95 grams of water. Well, that's only 3 sig figs, 2 decimal places. Okay, we can figure out the volume of the picnometer like we did last time. And so if we take this number and multiply it by the inverted density, we got 1 milliliter of water weighs 0.9982 grams. And the volume of the picnometer will be the same as the volume of the water. So this is going to be 9.95 divided by 0.9982. $9.9679 milliliters. Okay, I'm allowed how many sig figs here? Actually, just 3. And so this is going to come out to 9.97 milliliters. To the volume of the picnometer. When 10.20 grams of lead is placed in the picnometer, and the picnometer is again filled with water at 20 degrees C, the total mass is 44.83. So we got 44.83 grams total. And we're going to have lead in here, PV solid, and water. The amount of lead that they put in here is 10.20 grams of lead. 10.20 grams of lead. What is the density of lead in grams per cubic centimeter? The density of lead is, we need the mass of the lead divided by the volume of the lead. The mass of the lead is given. We have 10.20 grams of lead. Well, what is the volume of the lead? The volume of the lead we don't know. So we're going to have to figure it out. How can we figure it out? One way to figure it out is we know the total mass. And so if we have 44.83 grams total, then that's going to equal the grams of picnometer plus the grams of water plus the grams of lead. We know how many grams the picnometer is. It's 25.60 grams of picnometer. And we know how many grams of lead. We have 10.20 grams of lead. And so the only thing we're missing is the grams of water. This is our unknown. So let's go ahead and solve for grams of water. Grams of water will equal 44.83 minus 25.60 for the picnometer minus 10.20 for the lead. And so 44.83 minus 25.6 minus 10.2. And I get 9.03 grams of water. And so that means I have 9.03 grams of water. Here. Well, if I know how many grams of water I have, then I can figure out what the volume of water is by using the density. And so let's go ahead and use the density of water as 0.9982. And so I'm going to take my 9.03 grams and a milliliter per 0.9982 grams. And this will tell us how many milliliters of water we have. So 9.03 divided by 0.9982. And that gives us 9.0463 milliliters of water. How many sig figs am I allowed? I'm allowed 3 sig figs. So this is going to be 9.05 milliliters of water. And so I have 2 choices here. One, I could carry extra digits. You know, this isn't my final calculation. I'm allotted one rounding step. And so I've already rounded twice here. So what I'm going to do is I'm going to use these numbers here to minimize rounding error. We always try to minimize rounding error. Let's say you earn 49 cents a day from the bank, which would be pretty good. 49 cents is almost 50 cents a day. But let's say they wanted to pay you to the nearest dollar. So if you had 49 cents and you need to round it to the nearest dollar, how much does that come out to? $0. So let's say the bank wanted to round that every day. So every day you earned 49 cents, but every day they wanted to round it. So every day they'd round it to 0. So by the end of the year, how many dollars would you have? You'd have $0. And so that's rounding every day. However, what if you just added all the 49 cents and then rounded it at the end? If you did that, then you'd end up with like, $180 by the end of the year, right? Something like that. And so this is why we try to minimize rounding. A lot of people don't. A lot of people argue this. Sometimes you're high, sometimes you're low. So even if we do rounding, sometimes you round up, sometimes you round down, and the average is out in the end. But sometimes it doesn't. If you're always rounding down for some particular reason, it's somewhat random. And so anyway, we try to avoid rounding. So what I'm going to do is I'm going to just plug it in. The volume of the lead, well, we know what the volume of the picnometer is. It's going to be 9.96. So we have 9.9679 milliliters of picnometer. And then we're going to subtract the volume of the water. The volume of the water is going to be 9.0463 milliliters. 9.0463 milliliters of H2O. So if I have the total volume and I subtract the volume of the water, the remaining volume must be the volume of the lead. That is, the total volume is equal to the volume of the water plus the volume of the lead. And therefore the volume of the lead will be just the total minus the volume of the water. And what is that going to come out to? So we got 9.9679 minus 9.0463. Okay, I'm allowed, how many decimal places am I allowed? 2 decimal places, it looks like. So I'm going to have to round this to 2. So it's going to come out to 0.9216 milliliters. And so this is going to be 10.20 grams divided by 0.9216 milliliters. So let me go ahead and invert that and multiply by 10.2. And I get 11.0677 grams per milliliter. I'm only allowed 2 sig figs, so this is going to round to 11 grams per milliliter. This is my final answer here. And so the density of lead is 11 grams per milliliter. happened to the projector? Okay, there are a lot of density problems here because, so this is biased towards density problems. So let's take a look at 81. Hopefully 81 is not a density problem. 81, the Greater Vancouver Regional District chlorinates the water supply of the region at the rate of 1 ppm. That is 1 kilogram of chlorine per million kilograms of water. So we got 1 ppm chlorine. Which is equal to 1 kilogram of pure chlorine per 1 million kilograms of water, or total. This isn't how I wrote it before. How did I write it before? Remember the swimming pool problem? How did I write 1 ppm before? Yeah, I wrote 1 gram of chlorine per million grams of water, or solution, or total. Pool water is what I wrote. Or you could say 1 pound of chlorine. There's going to be 1 pound of chlorine for every what? For every million pounds of water. Although this is a bit tricky because pounds and grams are different. Gram is mass, pounds is weight. But it's all right. So I don't like these other units. Like I don't like pounds per pounds or kilograms per kilograms. I like grams. So I'm just going to use this. Even though they give us this, I'm going to use this. Because I like to write it the same way each time, you know, which is good and bad. I mean, it's easier to remember, but you know, there are other ways of doing it. You don't want to get stuck. The chlorine is introduced in the form of sodium hypochlorite. What's the formula for sodium hypochlorite? Which is bleach. NaClO. NaClO is correct, but it's usually written on, if you look at a bleach container, NaOCl. Kind of the same thing. Good, you remembered. Everybody remember hypochlorite? Hypochlorite is ClO charge? -1. Do you know the series? If hypochlorite is ClO -1, what is chlorite? ClO2 -1. That's correct. That's chlorite. What's chlorate? ClO3 -1. What's perchlorate? ClO4 minus. So sodium hypochlorite is, they take this salt and mix it with water to make bleach. And so they add a little bit of bleach to water. You'll smell the bleach or you'll smell the chlorine. You know. When I was young, I drank lots of tap water. In Santa Barbara, the tap water was chlorinated. And so there's strong odor of bleach or chlorine. It's just to kill any microbes in the water. But I got used to drinking bleach water. Obviously, you don't want to drink household bleach because the concentration is way higher than 1 ppm. But at 1 ppm, I've drank a lot of water. So I know the taste of 1 ppm chlorine. Fortunately, they don't use chlorine anymore. You know what they use? Iodine's going to leave a taste too. Iodine, I know the taste of iodine very well because, you know, iodine, povidone iodine. Povidone iodine, I used to make a 10% solution. I still do. And suck it up my nose. And you suck it up your nose and you gargle it. And that's to kill any microbes there, good or bad. Hopefully the bad ones. And so this is like what some countries did during COVID. You know, there's supposed to be this huge disaster in India. Oh, they're running out of oxygen tanks. Do you remember that? Yeah. And then you didn't hear anything about India or Sri Lanka or any of those places. Now, what did they do? Did they all die? Well, it turns out that no, they were doing, like I guess in Sri Lanka they were doing povidone iodine, you know, aspiration and gargling. Aspiration through your nose. So if you breathe it up through your nose, it's like getting a nose full of swimming pool water. That's what it tasted like and smelled like. But anyway, bleach we use to kill whatever, algae and bacteria and whatnot. The chlorine is introduced in the form of sodium hypochlorite, which is 47.62% chlorine by mass. And so this is 47.62% chlorine. If it doesn't specify, then we're going to assume it's by mass. Did it specify? No, it didn't specify, so we'll just assume it's by mass. If it's by mass, that means that sodium hypochlorite consists of 47.62 out of 100 what? 47.62 what? Out of 100 what? 47.62 grams of chlorine for every 100 grams of sodium hypochlorite. Okay. The population of the GVRD is 1.8 million persons. So we have 1.8 times 10 to the 6th people. If each person uses 750 liters of water per day, so each person uses 750 liters of H2O per person per day. How many kilograms of sodium hypochlorite must be added to the water supply each week to produce the required chlorine level of 1 ppm? This is a bit tricky here because remember the swimming pool? If we add, what happens to the volume? It increases, so this is another 2 unknown. We need to know what the new volume is after adding the sodium hypochlorite or the bleach. And we need to know how much sodium hypochlorite we need to add. Well, they're going to add solid sodium hypochlorite, not a liquid bleach solution. And so if we add solid sodium hypochlorite, what we're going to do is we're going to assume this. We're going to assume that when you add the sodium hypochlorite solid, it doesn't change the volume significantly. And that's going to make it from a 2 unknown to a 1 unknown problem. And so we assume that the addition of NaOCl solid does not change the volume significantly. And that's a reasonable assumption because the solid isn't going to change it much. It's just going to dissolve in there. It should be all right. Oops, sorry, habit. All right, so this looks like this is a straight dimensional analysis problem. What are we going to start with? Typically, we want to start off with the extensive, not intensive. Intensives are usually used for conversion factors. So what do we want to start with?
The amount of people.
Yeah. Let's start with this. 1.8 times 10 to the 6 people. 1.8 million people. Okay, then we need to get rid of people. How can we do that?
The water pay.
Yeah, the water per day. And so this is 750 liters of H2O per person per day. Oops. I didn't want to do it that way. The people aren't going to cancel. It's going to be 750 liters of water per person per day. I don't know why I inverted it. Just have it. So the people cancel. And that leaves me with water per day. So this is how many liters of water I need per day. But now I got to get rid of liters of water or days or what? Let's try to get rid of liters or liters of water. Is there anything with liters or liters of water? This one, but this is going to be in circles. I don't have anything. So I need to get rid of liters. Where can I go from liters? Yeah, let's get a milliliter. So 1,000 milliliters per liter. And so liters of water, now I have milliliters of water. Where can I go for milliliters of water? Where can I go for milliliters of water? I can, yeah, maybe I could go to grams, but it's not given. I have to assume something. So I'm going to make another assumption. I'm going to assume what? In order to go from milliliters of water to grams of water, I need to know the density. So I'm going to assume the density. I can assume the density of 1 gram per milliliter safely, but 1 gram per milliliter is how many sig figs? It's not infinite because water is not exactly 1 gram per milliliter. This would be 1 sig fig. Is it safe to assume the density of water is 1.0 grams per milliliter? 2 sig figs. Yeah, I think that's safe. But I want 3 sig figs because I'm given 2 sig figs here. Is it safe to assume the density of water is 1.00 grams per milliliter? Not if it's at 20 degrees. If it's at 20 degrees, what was the density? To 3 sig figs. 0.998. And so it's only a 1.00 in a small temperature range. So it's probably not safe to assume 3 sig figs, although sometimes we do. And so I think 2 sig figs is safe here. So I'm going to assume the density of water is 1.0 grams per milliliter. And so this is an example of we're missing something, but we just had to make an assumption, otherwise we can't solve the problem. And so we're just going to assume the density of water here. And so that's going to give me grams of water. Is there something that gets rid of grams of water? Yeah, 1 gram of chlorine per million grams of water. And so we get rid of water altogether, and now we're at grams of chlorine. Is there something that gets rid of grams of chlorine? Yeah, this should get rid of grams of chlorine here. Just flip it over. And so I'll have 100 grams of sodium hypochlorite per 47.62 grams of chlorine. So grams of pure chlorine cancel, and that gives us grams of sodium hypochlorite. What do they want the mass to be? They want it in kilograms of sodium hypochlorite. So I'm going to convert grams of sodium hypochlorite to kilograms. And so 1 kilogram is equivalent to 1,000 grams. And so now I have kilograms of hypochlorite, sodium hypochlorite per day. But I don't want it per day, I want it per week. And so let's get rid of days next. And so we know that there are 7 days in a week. And so the days cancel, and that gives me kilograms of sodium hypochlorite per week. And that's what they want. So let's go ahead and calculate this. .8 times 10 to the 6 times 750 times 1,000 divided by 1 million times 100 divided by 47.62 divided by 1,000 times 7. And so I got 1.9845 times 10 to the 4 kilograms per week. Kilograms of sodium hypochlorite per week. How many sig figs am I allowed? 2. So let's round this. This is going to be 2.0 times 10 to the 4th kilograms of sodium hypochlorite per week. In other words, this is going to be 20,000 kilograms per week. $20,000 kilograms, that's a lot. But I guess 1.8 million people, that's also a lot. The density of water changes a little bit. You know, it's not a huge error. You know, rather than let's say 1,998. You know, it's not huge. But other things have a more significant change with temperature. I remember at the lab at UCSB, the lab at UCSB is in these old Army barrack type building. The insulation isn't very good and the ventilation isn't very good, the HVAC system. And so the temperature would fluctuate a lot during the lab. And so at one moment it's warm. And one of the guys was measuring the volume of acetone. And so when the temperature of the lab warmed up, the acetone expanded. And when the temperature of the lab cooled down, the acetone contracted. You could actually physically see it expanding and contracting because the volume changed there. So I always wondered, you know, now gasoline is so expensive. And gasoline's measured by volume. It's not measured by mass. It would be better to measure it by mass. Because does the mass change with temperature? No, the mass doesn't change. But the volume does change. And so if it's a hot day outside, are you getting your money's worth of gasoline? Because on a hot day, the gasoline should expand, meaning you get less per gallon, less gasoline per gallon. And so I thought, well, maybe it's best to fill up the tank of the car when it's cold outside. You know? Or does it automatically calibrate? I always wondered, is that does it adjust the calibration depending on the temperature? I don't think they care that much. You're right. Yeah, there's a rubber line, but I don't. There's a calibration mark on there, and the calibration is for a specific temperature. But I think maybe on a hot day it's going to be less. Well, I never cared enough to fill up at a specific time, but maybe someday. Mike. Well, anyway, number 82, a Boeing 767 due to fly from Montreal to Edmonton required refueling. Because the fuel gauge on the aircraft was not working, a mechanic used a dipstick to determine that 7,682 liters of fuel were left on the plane. The plane required 22,300 kilograms of fuel to make the trip. In order to determine the volume of fuel required, the pilot asked for the conversion factor needed to convert a volume of fuel to a mass of fuel. The mechanic gave the factor as 1.77. Well, if we want to convert volume to mass, we need the density. So this has got to be the density. But the density of fuel changes with temperature. And so the first thing is that the correct density for that temperature? Well, let's assume it is. Let's assume that the mechanic has a table, and when they looked at the table, this is the correct density for that temperature. And so here they care about it. I hope they care about it, because I hope they would determine what the temperature is and then figure out how many gallons or how many liters of fuel they need. Because there it would make a difference. Assuming that this factor was in metric units, okay, this problem is different because there's no units here. What is that, grams per milliliter? Okay, assuming that this factor was in metric units, kilograms per liter. Well, kilograms per liter is the same as gram per milliliter. It's going to be numerically the same. And that's what you'd expect. The pilot calculated the volume to be 4,916 liters. This volume of fuel was added, and the 767 subsequently ran out of fuel, but landed safely. This is a true story, by gliding into Gimli Airport near Winnipeg. And so the calculation was off. The error arose because the factor 1.77 was in units of pounds per liter. What volume of fuel should have been added? And so what we're going to do is we're going to assume the density is correct, for the temperature. And this is good that they're trying to figure out the mass rather than the volume, because volume changes with temperature. Mass does not change with temperature. And so when you fuel up a plane, you want to fuel it by mass, not by volume. When we fuel the car, we don't fuel by mass, though. We fuel by volume. But a car, the consequences are a lot less severe. Run out of gas. So let's see. 22,300 kilograms. So at this temperature, what is the liters of fuel here that we require? So we have kilograms of fuel. What we need to do is just some dimensional analysis. We need to get rid of kilograms or kilograms of fuel. There's nothing that gets rid of kilograms of fuel, so we're just going to convert it to grams. Okay, so now we have grams of fuel. Well, there's nothing that gets rid of grams of fuel, but we have something that gets rid of pounds. So let's go from grams to pounds. And so there's 453.6 grams in a pound. And so now we have pounds of fuel. Now we can use the density here. The density is in weird units. It's 1.77 pounds of fuel per liter of fuel. That was the correct units for this, pounds per liter. Okay, now we have liters of fuel. So let's see how many liters of fuel are required at this particular temperature. So 22,300 times 1,000 divided by 453.6 divided by 1.77. And so this required 27,775 liters of fuel. Now, how many sig figs am I allowed here? 3. But I'm not going to round this, because if I end up rounding down, then I might run out of fuel if I round it down. If I round it up, then that's fine. But I'm not going to round it just yet. And so that's the amount of fuel required. How many liters of fuel was on board? And so 7,682 liters in tank. And so how much are we short by? 27,775 minus 7,682. We're short by 20,093 liters of fuel needed. And so they were way off. They only added 4,916 liters, whereas 20,000 liters should have been added. '83. The following equation can be used to relate the density of liquid water to Celsius temperature in the range 0 degrees C to about 20 degrees C. All right, where did this equation come from? That equation allows you to calculate the density of water at any temperature. And this is an empirical equation, so let me show you. So what people do is they measure. Do you know what the density of water at 4 degrees C is? The density of water at 4 degrees C is 1, right on 1. So 4 degrees C, 1 gram per milliliter is right on. But when we go to 5 degrees C, 6 degrees C, it starts to deviate off. In fact, you see the density peaks at 4 and then drops as you go higher and higher in temperature. But this is a weird relationship, because at 3 degrees C it drops. And so from 0 degrees C up to 4 degrees C it goes up and peaks at 1. And then as you increase the temperature, it drops down. And so if we were to look at the pattern or the trend for this, we'll take all this data and graph it. And when we graph it, it looks like this. Although you can't see it here, it goes up and then down. So as it goes up and then down, it looks like a parabola. You know, what's the mathematical equation that fits a parabola? Like a squared equation, or second order, or quadratic. And so all we do is we figure out the equation for this curve, and that's this. So this is the equation for the parabola. It's a little weird. It's a little weird because they're using the Celsius temperature rather than the Kelvin temperature. If they use the Kelvin temperature, it would be a bit cleaner. But since we measure it in Celsius, it's easier. So this equation came from experimental observations. And since it came from experimental observations, we call it an empirical equation. So this would be the law of the density. We could also try to derive this not from observations, but from what? This is the two-pronged approach. One, we can come from observations. The other direction, we can come from theory. So we could try to derive this from theory. It'd be a lot harder. And we aren't going to do that. And so all we do is once we have a law of the density, then we just use it. To use it, to 4 sig figs determine the density of water at 10 degrees C. So 10 degrees C, you plug in 10 degrees C for T. You see there are no units here. This is an engineering equation, so we just plug in 10 here. And then calculate the density. You got to make sure it's degrees C. This is how they screwed up the fuel on the plane. There are no units there. And so you have to know what units to use. And so if you plugged in Kelvin here, you'd be way off. And so that's just plugging algebra. B, at what temperature does water have a density of 0.99860 grams per cubic centimeter? So here we plug in 0.99860 grams per cubic centimeter, and then we solve for T. If we solve for T, then we have to use what formula to get T? We need to use the quadratic formula. This is a second order. So what we'd have to do is we plug in that, and then we get this into quadratic form. Quadratic form is ax squared plus bx plus c is equal to 0. And then we plug in a, b, and c into our quadratic formula and then solve for x. X is going to be t. And so we use the quadratic. That's not so easy because look at how many sig figs. 5 sig figs here, a bunch of decimal places here. The numbers are quite big. It's not simple like 2x squared plus 4x plus 2 is equal to 0. You know, that's easy to plug into the quadratic. When you have these numbers, it's a pain. And so this is why I like the calculator so much. You know, a calculator that solves the quadratic for you, it's easy to plug in all these digits, calculate the answer, rather than doing b squared minus 4ac, square root of that, etc. Okay, C, in the following way, show that the density passes through a maximum somewhere in the temperature range. You know where it hits the max? At 4 degrees. And so if we graph it, we can see it. So number 2, graph it. And so the way they graphed it is they calculated the density every 5 degrees. So every 5 degrees from 0 to 100. And then they graphed it. Then they looked at where it peaks. It peaks at 4. So between 0 and 5 degrees, it seems to peak. So then they went to 1 degree increments. In 1 degree increments, they calculated. This is a lot of work because you're doing so many calculations. And so they did a bunch of, like 20 calculations to generate the graph and then figure out where the peak is. By estimation, can you look at this and see that the density is going to max at about a T of 4? No, that's pretty hard. I'm not sure how they estimated it. And so by estimation, I'd read it, how they estimated it in the solutions guide. Let's see. 3, by a method based on differential calculus. Differential calculus is not required for this class. But this is something that's commonly done, finding a maximum function or minimum of function. And so this is our function. We find the max of the derivative, what we call the first derivative of that function. But this is a lot of busy work, so I'm not going to do that. '84. A piece of high-density styrofoam measuring 24 by 36 centimeters by 5 centimeters floats when placed in a tub of water. When a 1.5 kilogram book is placed on top of the styrofoam partially sinks, as illustrated. Assuming that the density of the water is 1.0. See, they're assuming 3 sig figs here. It's only 3 sig figs in a pretty narrow range. How good is 3 sig figs for the density of water? So we look. Well, from 4 degrees, no problem, 1.00. How about at 5? If we round that to 3 sig figs, that's fine, 1.00. 6, that's fine. Let's drop down here. If we go to 13, we round this to 3 sig figs, what would that round to? 0.999. 12 would round to 1.00 to 3 sig figs. And so maybe between 0 to about 12 degrees, it's 1.00. And then from 13 on, it's 1.0. And then when we get to, let's say, 32, if we round that to 2 sig figs, it's 1.0. But if we round this to 2 sig figs, it's 0.99. So 1.0 is good to about 32 degrees. Well, 32 degrees is pretty warm water. So assuming you're just using room temperature water, we're okay to 2 sig figs here. 12 degrees C water is kind of cold, right? Because room temperature is about what? Room temperature is about 25 degrees C. And therefore, if we're dealing with room temperature water, I would feel comfortable with 2 sig figs, 1.0 grams per milliliter. Does that make sense? Rather than this. But here, it's all right. They're telling us to use 3. So, so maybe this is very cold water. It's fine. What is the density of the styrofoam? So, do you know about buoyancy? What is it? Is it Archimedes? You know, if you have something like this, the volume of water displaced is equal to the mass. So let's say you displace 10 grams of water, you know, by sinking, 10 grams of water gets pushed out, then that must mean it must weigh 10 grams. Have you heard that before?
Yeah.
Okay. Well, that's physics. There's no talk about that in this chapter. And so let's skip this problem. Okay, we're going to skip this problem. '85. A tabulation of data lists the following equation for calculating density D of solutions of naphthalene and benzene. So we have a 2-component mixture, like we had ethanol and methanol. And what they did was they came up with the equation for us. At 30 degrees C is a function of mass percent of naphthalene. And so the density changes depending on how much naphthalene we have. If this mixture were 100% naphthalene, we plug in 100 here, 100 here, we get the density. If this mixture were 0% naphthalene, we plug in 0 here, and then calculate the density. So we can go from 0% naphthalene to 100% naphthalene, and this is the equation that describes it. But this equation is not, you know, what we had earlier is we had a linear change in going from 0% ethanol to 100% ethanol. Remember, it was a linear change. This one is nonlinear, and that's because of the way these organic molecules pack together. And so it gives a nonlinear, because it's squared. And so this is a bit more complicated, but we could still use the graphical method, but we need to calculate some more points to determine the curve. Use the equation above to calculate A, the density of pure benzene. Well, pure benzene is going to have 0% naphthalene, so just plug in 0, 0, it's 1 over 1.153 grams per. The density of pure naphthalene, we'll plug in 100 here, we can calculate it. The mass percent of naphthalene in a solution that has a density of 0.952. Okay, so if the density is 0.952, this is a quadratic. So we'd have to get it in a quadratic form, and then we would need to use the quadratic equation. So they can give us a hint here. Hint, for D, you need to use the quadratic formula. See section A3 of Appendix A for what the quadratic formula is. I don't know why they didn't give this hint in the earlier problem, because we had to use the quadratic in the earlier problem as well. We're not going to do this. This is just algebra. 86. I assigned 86, but now I regret assigning it. I must have thought this is an interesting problem because, you know, this is one of those things people always talk about. People always talk about the rise of sea level with global warming. So, anyway, the total volume of ice in the Antarctic is about 3.01 times 10 to the 7th cubic kilometers. If all the ice in the Antarctic were to melt completely, estimate the rise H and sea level that would result from the additional liquid water entering the oceans. The densities of ice and fresh water are 0.92 grams per cubic centimeter and 1.0. Here they use 2 sig figs. Even though melted ice would be cold, if it's cold, I think the temperature is going to be low. But maybe, near the Antarctic, the ocean's pretty cold. I don't know how cold, but maybe 3 sig figs would have worked here. But it's all right. 2 sig figs you can feel comfortable with, respectively. Assume that the oceans of the world cover an area A of about 3.62 times 10 to the 8 kilometers squared, and that the increase in volume of the oceans can be calculated area times height. So this is very similar to earlier problems, so that's good. We just have to calculate the height, and so we just need the volume. The volume, we just got to figure out the mass that dissolves. Or actually, we have the volume of ice, which is going to give us the mass of ice. And from the mass of ice, we'll get the mass of water, and from the mass of water, we can get the volume of water. That kind of thing. But then I thought, maybe this problem's not so good, because I just saw this picture of an iceberg passing Newfoundland. And they said this iceberg was 200 feet tall. And it was a pretty impressive picture. But if the iceberg is 200 feet tall, is that it? No, because underneath the ocean, it's where the bulk of the iceberg lies. And so who knows how big it is down here. And so the only way we could solve this is assuming that the ice floats on the surface unless we calculate how much of the ice is underneath. I don't know if they want us to do that. Maybe they do, but then we're already displacing water, and then we've got to refill the water. And so this problem is turning into a physics problem, primarily. And so I don't think it's so good anymore. 86. This is going to overestimate it based on the assumptions we make. Because the assumptions we make is this whole ice is floating on top, and it's not sunk in at all. And so this is going to be a large overestimate. I hope this isn't the way they calculated it in the projections, because if this is the way they calculated in projections, then I think the projections are way off. So skip 86, even though I signed it, just skip it. 87. An empty 3.00 liter bottle weighs 1.70 kilograms. '87. I don't know how this got into the advanced section, because this is a pretty basic problem, I think. It's 3.00 liter bottle, and it weighs 1.70 kilograms. Empty. Filled with a certain wine, it weighs 4.72 kilograms. So now we fill this with wine. It weighs 4.72 kilograms. The volume is 3.00 liters still. The wine contains 11.5% ethyl alcohol by mass. Ethyl alcohol and ethanol are the same thing. And so 11.5% means 11.5 grams of pure ethanol, ETOH, per 100 grams of what? Of wine. How many grams of ethyl alcohol are there in 250 milliliters of this wine? So we have 250 milliliters of wine. That's the extensive property, so we'll start with that. And then we got to get rid of milliliters and milliliters of wine. So where should we go here? Well, where we should go is, why did they give us this data here? They gave us this data so that we could determine what? The density. So let's go ahead and determine the density. 4.72 kilograms is 4,720 grams. 3 liters is 3,000 milliliters. So I'm just going to convert it in my head since it's an easy conversion. And so this is going to be 4,720 divided by 3,000. And the wine is pretty dense, 1.573 grams per milliliter. I'm allowed 3 sig figs here, but I'll carry 1 extra. And so I get 1.573 grams per milliliter of wine. And so milliliters of wine cancel, that gives me grams of wine. Did I get that correct? No, I didn't. This would be extremely dense wine. It'd be like really thick. You know, wine is kind of watery, isn't it?
Ports are thicker. Ports are thicker. They're
Yeah.
probably more dense.
Yeah. Could be. I mean, this is almost like, yeah, this is going to be 1.5. I mean, if you think of the diatomaceous earth, the diatomaceous earth was 2 grams. That's glass. The glass is like 2 grams per milliliter. So did I make a mistake? Can you see, did I make a mistake? This seems awfully high.
Oh, Professor,
Uh-huh.
you used the 3 liters instead of the 1.78 kilograms. Yeah.
Okay, it is 3 liters. The bottle didn't change.
Just subtract the weight of the bottle.
Yeah, I forgot to subtract the weight of the bottle. That's what I did. So I need to get the weight of the wine. Are we out of time?
Yeah.
Oh, shit. I got behind. And so I did make a mistake there. But we'll continue. I was going to have the quiz today, but we'll have the quiz tomorrow.